Hello. So this will be our review for test 2, which is just chapter 13. And so I'm going to pull these questions from the practice test, right? Practice test 2, that is. And the first question is just find the domain of the function f of xy equals tangent of x divided by the sine of y. So tangent of x naturally has a domain of set of all x such that x does not equal pi over 2 plus any multiple of pi, right? And notice that sine of y is in the denominator. So where's the sine of y equal to 0 for all y that are just multiples of pi, right? So putting them both together, the domain is the set of points in the xy plane, right, because it's a function of two variables, such that, I know the book uses a colon, I use a vertical bar, doesn't, same thing, such that x does not equal pi over 2 plus n pi, and y does not equal n times pi, right? So n is just any integer. We can mention that, where n is any integer, positive, negative, 0, right? So that's it for number 1. And then for number 2, I think the only one I'm going to do is part C because there's a typo in the answer key. So 2C, we want to calculate the limit as x and y approaches 0, 0 of x squared minus y squared over x minus y. Right? And you do it the usual way, right? X squared minus y squared is just x minus y times x plus y divided by x minus y. So we can cancel x minus y. And now we're just taking the limit as x and y both go to 0 of x plus y. So 0 plus 0 is indeed 0. So the answer should be 0. Right? Yeah, so the answer key says does not exist. I'm not quite sure where I got that answer, but it's wrong. So the limit clearly does exist, and it's just 0. There's one very subtle point here, however, right? Remember, the whole idea of the limit is that it has to approach the point, in this case 0, 0, along any direction, right? And in fact, there is one bad direction where y equals x. Try to get that right. Right, along this line y equals x, you can't have points where y equals x because then the denominator would be 0. So any point on this line, right, does not count. It's not in the domain. Right? In other words, the domain here is the set of points such that x does not equal y, right? But that's just one bad line. Every other direction is fine here, right? So as long as your path does not cross that line, let's say, or it can cross the line, just not multiple times, right? Not infinitely many times, for example. So I think that's the only issue, but nonetheless, if you look at the definition of the limit, right, involving the distance to the origin, it should work out. You should get 0 there. So the answer should be 0 instead of does not exist. So there's one typo. There may be others going forward, right? Number 3, those are just partial derivatives. I think you can handle those. Well, we'll do number 4. Number 4 is x e to the xy plus y e to the x. And we want to find both first partial derivatives. So let's find the x partial derivative. Or if you prefer, partial of f with respect to x. So now y is the constant, right? So we're going to get x times x squared, e to the xy, right? Wait. Y is the constant, right? Yeah, if y is the constant, x is the variable, it's x times y, e to the xy, right? And then plus y, e to the x. Okay. Yep, I was going backwards here, right? Here, x is the constant, y is the variable. So the partial of e to the xy with respect to y is x e to the xy. So now x times x is x squared, e to the xy. And then the partial with respect to y is just 1 times e to the x. Okay, so I think these are right. No, they're not right, because I forgot the product rule here. Right, when you're doing the derivative with respect to x, in the first problem here, it's x times the derivative of x e to the xy, which is xy e to the xy, plus e to the xy times the derivative of x. All right. Now I think it's right. At least that's what's in the answer key, so I think that's correct. And you can factor out the e to the xy, but it's not necessary. Shoot. All right, so that's number 4. Yeah, a little tricky. You got to remember the product rule and chain rule and all that. So we better do number 5, right? F of xy is defined as the definite integral from x to y of 12t squared minus t to the negative 1 dt. So for part A, you're just plugging in 1 and e, right? In other words, you're just calculating the definite integral, which is a Calc 1 problem, to be fair, but it's a good review, right? So this is just going to be, let's see, divided by 3. So 4t cubed minus log of absolute value of t. And when you plug in the 1 and the e, we're going to get 4e cubed minus log of e is 1. And then minus 4 times 1. And then minus a negative is plus log of 1, which is 0. So I think we just get 4e cubed minus 5. Okay. And then for b, we need the partial derivative with respect to x. So we have two choices here. You can use the second fundamental theorem of calculus, or we could evaluate f of xy directly by using the first fundamental theorem of calculus. After all, we did most of the work already. Just use x and y here. So this is going to be 4y cubed minus log of y minus 4x cubed plus the log of x. And we can write this many ways. This is 4 times y cubed minus x cubed plus log of x divided by y. Right? Now take the partial with respect to x. And you just get negative 12x squared plus, and then by the chain rule, I think we get a 1 over y times the natural log of x. X over y still. Okay, so I think that's right. Right. And then with respect to y, very similar. Here you're just going to get 12y squared. And then with respect to y, x is the constant. So we're going to get plus x. So the derivative of x over y squared is negative x over y squared, right? Yeah, so negative x over y squared times the natural log of x over y. Yeah, so I think that's it. So 12y squared minus x over y squared log of x over y. Nope. Just checking the answer, and that's not even close. So I think what I'm doing is I'm treating both of these as variables, and obviously you're taking the partial derivative, right? So yeah, let me fix this. Okay, so the first term's correct, right? The derivative of log is just 1 over, right, x over y. So 1 over x over y is y over x. And then times the derivative of x over y. The partial derivative of x over y with respect to x is just 1 over y. So that's negative 12x squared plus 1 over x. The y's cancel. And then for part C, now with respect to y, right, so we still get y over x, and then times the derivative of that, so that was negative x over y squared. So you just get 12y squared minus 1 over y. So I think that's it. Okay, so let me fix that up here too, right? So this is x to the negative 1 minus y to the negative 1. All right, so now that should do it. Okay. Sorry about that. Yep, see, even I get confused with partial derivatives and total derivatives, and there's all kinds of derivatives. There's something called a covariant derivative and a normal derivative. It goes on and on. Oh well, but we don't have to worry about that in most cases. Okay, so I'm skipping 6. I hope that's fairly routine. And in any case, it's explained in the answer key, I think, a little bit. So number 7. W is x times sine y plus the tangent of z. Find dw. Remember, dw is the total differential of w. So by definition, and this is on your formula sheet, so you can look it up, it's the partial of w with respect to x times dx plus the partial of w with respect to y times dy. And we do have this is a function of z, so we also need a partial of w with respect to z times dz. Right, and just taking the partial derivatives, and I know I'm not very good at that, right? But with respect to x, I think we just get sine of y times dx. And then with respect to y, x is a constant, so we get x times cosine of y times dy. And then the derivative of tangent is secant squared of z times dz. Got it? But if you want, we can do number 8 as well. It's the same idea here. So here, z is x squared times the sine of xy squared. And here we want to find dz. Right. So the definition is dz is the partial of z with respect to x times dx plus the partial of z with respect to y times dy. Right? Because it's only a function, z is a function of x and y only. It's not a function of z like number 7 was, right? Okay, so fool me once, right? This is going to be a product. So product rule, right? First times the derivative of the second. And the derivative of sine is cosine. And then the derivative of xy squared is y squared, right? Plus second times the derivative of the first. So 2x times sine of xy squared. All times dx, right? And then do the same thing for the partial with respect to y. Luckily now x is a constant, so this is x squared. And then the derivative of sine is cosine. sorry, I'm writing too small here, so x squared times cosine of xy squared, and then the derivative of xy squared is 2xy times, sorry, dy here. All right, let's write it all out here, right? So this is going to be x squared y squared times the cosine of xy squared plus 2x sine of xy squared, all times dx, plus 2x cubed times y times the cosine of xy squared times dy. So that's the answer in the answer key. So we'll go with that. Number 9, pretty standard, and I did one like that in the video for that section. Chain rule, I think, was 13.5. So maybe let's do number 10. And I kind of remember doing one like that as well, but okay. So w is a function of x and y. It's x squared times y to the 4th power. And x is some function of t, and y is some function of t. And we know the given values, right? X evaluated at 1 is 5. Y evaluated at 1 is -2. The derivative of x evaluated at 1 is 3. And the derivative of y evaluated at 1 is -1. And we want to find the derivative of w with respect to t evaluated at t equals 1. All right. So using the chain rule, you get the partial of w with respect to x times the derivative of x with respect to t, right? Plus the partial of w with respect to y times the derivative of y with respect to t. So the partial of w with respect to x is 2x y to the 4th. And then the derivative of x with respect to t, well, we don't know. We don't know what x is, right, in terms of t. So it's just x prime of t, right? Plus, the y partial of w is 4x squared y cubed. And then the derivative of y is the derivative of y prime, right? So now we can just plug in t equals 1, right? And the way we do that is everywhere I see an x, you change it to 5. Everywhere I see a y, you change it to -2. The derivative of x evaluated at t equals 1 is 3, and the derivative of y evaluated at 1 is -1. So plugging in all the numbers, we get 2 times 5 times -2 to the 4th times 3 plus 4 times x squared is 5 squared, right? Times -2 cubed times -1. And my calculator spits out, well, the first term is 480. The second term is 800. So I believe that's 1,280 as the answer. Okay, I think that's it. Number 11. We did one like this in the same section, in the chain rule problem, right? So we have e to the xz plus y times z is equal to 0. And we want to find both partial derivatives, z with respect to x and z with respect to y. Right? Oops, that looks weird. There we go, right? So, can we solve for z? Well, I can't. If you can, great, more power to you, but I've never been able to do that here. So if there's a way to do it, it's unknown to me. So, yeah, so we're going to have to make use of implicit differentiation, right? We're going to call this function f, capital F as a function of x and y. All right, let me just write it down again. Right, so capital F as a function of x and y, and z, and z, right, is e to the xz plus yz, and that equals 0, right? So using the formulas for implicit differentiation, the partial of z with respect to x is going to be negative partial of f with respect to x divided by partial of f with respect to z. So what are the partial derivatives? So with respect to x, you're going to get z e to the xz. With respect to y, you're going to get z, I think, right? And with respect to z, you're going to get x e to the xz plus y. So here we're just going to get negative z e to the xz all over, say, y plus x e to the xz. Right, so that's for the x partial derivative. And then for the y partial derivative of z, it's minus fy over fz. So now it's just negative z over y plus x e to the xz. Okay. So yeah, you have to know your implicit differentiation. Again, it's all on the formula sheet. So if you don't remember these formulas, yep, just look them up. Okay, number 12. I think this is a fun one. We have a fluid moving through a tube of length 1 meter and radius, so the radius is 0.005 meters plus or minus 0.00025. Yeah, so the plus or minus, you're familiar with that if you've taken any physics or engineering courses, that this is the experimental error, right? So you could measure the radius of a tiny tube, but maybe not exactly, right? So that's the experimental error here, right? Under a pressure, so P for pressure, and this will be 10 to the 5th, which is 100,000. So 100,000 pascals plus or minus 1,000 pascals, right? And then the velocity v, for whatever reason, we know this exactly, 0.625 times 10 to the negative 9. And I know that's not scientific notation, right? It should be 6.25, right, times 10 to the negative 10. And this is in meters per second. Okay, and this is in pascals, which is a Newton meter per second. Wait, sorry, a Newton per meter squared, I think. And yeah, I'm pretty sure it's that. I'll just call it pascals. And then this is in meters, right? All right, so use differentials to estimate. We're trying to estimate, right, the relative error of the viscosity, which is the Greek letter eta here. Eta is pi over 8, times p r to the 4th over v. Okay, so that's given, right? This is given in the problem. And we're looking for the relative error. So remember, the error is d eta. And so for the relative error, you take d eta divided by eta itself. Okay. So, yep, a couple ways we could do this. Let's just find d eta and divide by eta, right? So d eta, it's just the differential. So we'll take the partial of eta with respect to r times dr plus the partial of eta with respect to p times dp. Okay. Now, if you're wondering, why am I not doing that? Because this is a function of 3 variables, right? It also depends on v. But notice that there's no plus or minus with the v. We know the velocity exactly. Don't ask me how we know that, right? I think we know, I mean, they just want us, they want this to be simple, right? So dv here is effectively 0. So we don't need this term at all here, right? We know v, this is exact. Okay, so yeah, as a practical matter, I don't know how we know that exactly, but we don't know r or p exactly. But in this problem, that's the idea, right? All right, so the partial of eta with respect to r is going to be, so the pi over 8 is just a constant. I think we can drag that all the way outside, right? So with respect to r, we get 4p r cubed over v times dr. Right? And then plus, with respect to p, this is just going to be r to the 4th divided by v times dp. Okay, so far? Well, now to get the relative error, we divide by eta. Okay, so I'm just going to copy all this down here. dr, this should be an r, plus r to the 4th b dp. And what's 1 over eta? So it should be 8 over pi times v over p r to the 4th. So I'm just going to multiply by 1 over eta, so 8 over pi times v over p r to the 4th. Okay, so notice what happens. These cancel, right? Pi divided by pi is 1, 8 divided by 8 is 1. So the pi over 8 doesn't matter here. And so what do we get when we distribute? We get 4p r to the 3 over v times v over p r to the 4 times dr. Right? So that goes with that. And then with this, we get r to the 4th divided by v times v over p r to the 4th times dp. I need the space over there, so let's write it over here. So notice what happens. We have v divided by v is 1, so the v's cancel, the p's cancel, and 3 of the r's cancel. So I think we have 4 over r times dr, or better yet, 4 times dr over r. Right? And then for the second term, again the v's cancel, and here the r to the 4 cancels, and we just get dp over p. Okay, so this is the relative error in its eta, in its most simplified form. And again, we didn't have to do this, but I think that might make things a little bit easier here if we have this version, because let's see, the error, so dr here, we never mentioned that, right? This is just dr, and this is your dp, right? So yeah, so for reference, dr is just 0.00025, and dp is 1000, and dv is 0, of course, because the velocity is exact, right? Oh, and r is presumably 0.005, and p is 10 to the 5th, or 100,000, either way. So plug all those in here, and right, so for the relative error d eta over eta, we get 4 times dr, 0.005, divided by r, which is 0.00025. Nope, I got that backwards. I'm sorry, dr goes in the numerator. So that's 0.00025 for dr divided by r, which is 0.005, right? And then dp is 1000 divided by p, which is 100,000. Yep, so calculator time. So the first term is just 0.2. And the second term is, well, 1 over 100, right? So 0.01. So you get 0.21, right? Or 21 over 100, depending on which way you want to write it. So that's the relative error in eta. Relative error for the viscosity. right? Or 21%, right? It's a 21% relative error. Either way. Yeah, so again, this is a fluid dynamics problem maybe. I don't know where this formula for viscosity comes from, but your physics or engineering professors will probably explain that. All right, number 13. I think this should be fairly routine by now. Taking partial derivatives and gradients and directional derivatives. And it might help. I'm going to rewrite the function this way, xy to the negative 1 plus yz to the negative 1, so I can use the power rule, right? So for the gradient, we just need the 3 partial derivatives, and so here they are. Right. And then for z, we just get negative yz to the negative 2, right? Okay, so for part A, the gradient as a vector, right, because the gradient is a vector, you just form the vector with these 3 components. So let's see, how should I write this? How about 1 over y times I plus 1 over z minus x over y squared, right, all times j, and then minus y over z squared times k. Right. All right, so you can write it with the bracket, the angled bracket instead. That's fine too. And then b, we want the directional derivative of f in the direction of u. I know that does look like an n, doesn't it? So u, remember u has to be a unit vector at the point 3, 2, 4. So u is a unit vector. You can check that, right? It's just the vector with components 1 over square root of 2, 1 over square root of 2. Oh, sorry, it's a vector in space, right? So the third component has to be 0. We need that here, right? Yeah, and its magnitude is 1. So the easiest way to calculate the directional derivative is just take the gradient at the point 3, 2, 4, dot product with u. So the gradient, well, let's plug in the 3, 2, and 4 here. If we plug in y equals 2, that's 1/2. Oh, shoot. This is going to be 1 over 4 minus 3 over 4. Oh, that's nice. So that's just negative 2 over 4. Negative 1/2 for the second component. And then, let's see, minus y over z. So that's minus 2 over 16. So minus 1 over 8. And then the dot product with, maybe I should rationalize the denominator here. I mean, you don't have to, but why not? Okay, so for the dot product, you're just going to get square root of 2 over 4 minus the square root of 2 over 4, and then minus the square root of 2 over 8 times 2 is 16. Oh, I'm sorry, never mind. Negative 1/8 times 0 is 0. Yeah, you just get 0 then. Okay, so the directional derivative is 0. Not the vector 0, right? This is a dot product. It is a scalar. Okay. All right, so that's number 13. And I typically get questions on 14 as well. So for 14, we're given a function of 2 variables, x and y, 4x squared plus 12y squared. And this is the surface of a paraboloid, but we don't really need to know that here. If we were to graph the surface, it would be a paraboloid. An elliptical paraboloid, but it doesn't matter, right? Anyways, part A, find the direction as an angle to the positive x-axis of the steepest descent at the point 2, 3, 124. And so what that means is we want to maximize the directional derivative of the function f as a function of theta, in terms of theta, right? Okay, so yeah, so we want to either maximize the directional derivatives. That's one way of looking at it. Or, hopefully you remember that the maximum directional derivative, right, is in the direction of the gradient. So we find that direction, take the gradient, not difficult. So it's just 8x and 24y, right? Oh, and at the point 2, 3, the gradient is an actual vector, 16, 72, right? So that should be the direction of the steepest descent, right? Now, the direction is given as a vector. But that's not what they want. They want an angle. Okay, so let's see. We have a vector with an x component of 16 and a y component of 72. So the angle with the x-axis, yep, just trigonometry, right? Opposite over adjacent. So opposite is 72. Adjacent is 16. Yeah, so this is just 9 over 2, 4.5. So the angle is just the arctangent of 9 over 2. 77.47 degrees. Okay, so there's the exact, again, that's a 9 over 2. And there's the approximate. And so that's it, right? Find the angle, find the direction as an angle, right? So if they want the direction as a vector, you can leave it like this. But because they want the angle here, you got to use the tangent function, right? All right, part B. Find all points xy such that the magnitude of the gradient, so here's the magnitude of the gradient, they want that to equal 120. So that would actually be the slope, right, in the direction of the steepest descent. So what points do we have that, right? Well, we already took the gradient, right? That's this vector here, so we can easily take the norm, or the magnitude of that gradient. It's the square root of, right, 8x squared plus 24y squared. So that's going to be the square root of 64x squared plus 576. Yep, 576y squared. Just making sure. Right, so where does this equal 120? Okay, so solve that equation. Let's start with getting rid of the square root. We can square both sides. No problem there. That's a 5, not an s, right? And 120 times 120, sorry, 14400, 14,400, right? Yeah, so that's it, right? All points that satisfy this equation here will be the points that have this magnitude of the gradient. Right. So you should know what this is, of course. If you divide both sides by 14,400, you get slightly more familiar equation. This is an ellipse. So every point on the ellipse has this magnitude. So to answer the question, it's the set of points x and y such that x squared over 576 plus y squared over 64, sorry, is equal to 1. So every point on the ellipse, right, has this magnitude of 120. The gradient has the magnitude of 120. And clearly I cannot do math in my head here. Yeah, so these are wrong. So the first equation was right. I'll fix the other ones. Okay, so 14,400 divided by 64 is 225, and 14,400 divided by 576 is 25. So, yeah, I was trying to do that in my head and I blew it. Sorry. Okay, so yeah, that's the equation of the ellipse then, and that's the answer and the answer key too. So, all right. All right, moving on to number 15 for the surface given implicitly as the function, or the equation rather, x squared y plus y squared z plus z squared x equals 10. And I have no idea what surface that is. It doesn't matter. It's some surface in space, right? So part A, find the equation of the tangent line. Sorry, tangent plane. I'm thinking Calc 1, right? Tangent plane is Calc 3. At the point 2, 1, negative 2, right? So what do we need for the equation of a plane? Well, yeah, we need a point, which luckily they give us, right? So this is just our x naught, y naught, z naught. And this is on your formula sheet, right? Or if it isn't, you probably should know it by now. So we already know x naught, y naught, z naught. We need the a, b, and c. So when you have your surface in space, right, at a given point, the tangent plane will also have the same normal vector, right, as the gradient of capital F, right? So we can use the gradient of f as our normal vector n. So let's just take the gradient. That's going to be, let's see, 2xy plus z squared. So that'll be the I component, the x component. And then for the y component, we're going to get x squared plus 2yz. And that'll be the j component, or y component. And then the z component will just be, let's see, y squared plus 2zx, 2xz, same thing, times k. Right, but we're at, right, specifically at the point 2, 1, negative 2. So when we plug in these numbers into the gradients, we get our normal vector n here. So 2 times 2 times 1 is 4. 4 plus 4 is 8. Let's see, 2 squared is 4, plus 2 times 1 times negative 2. That's negative 4, so 4 minus 4 is 0. That can happen. And then y squared is 1. 1 plus 2 times negative 2. Wait, 2 times 2 times negative 2. So 1 minus 8 is negative 7. So there's my a, b, and c. And I think you can take it from here, right? Plug in the numbers. Minus 7. Z minus negative 2 is z plus 2 equals 0. So we get 8x minus 16 plus 0. Minus 7 times z minus 14 equals 0. So 8x minus 7y minus 30 equals 0. Or equals 30. Well, I'll leave it this way. Like I say, I'm not picky about that. All right, so that's part A. Part B, find the equation of the normal line. So basically the line in the direction of this normal vector here. So this line here keeps going. So what do we need for the equation of a line? So let's say with position vector, x0 plus at, y0 plus bt, and z0 plus ct. Those are the parametric equations of a line. And luckily, the x0, y0, z0 were the same, and the a, b, and c are the same because we're using the same normal vector, right? Well, normal vector to the surface, to the tangent plane, but it's a direction vector for the line. The line will point in the same direction as that vector. So really, it's just writing down the equations, right? x0 was what? 2 plus 8 times t. y0 was 1 plus 0 times t, right? And then z0 was negative 2 plus c times, so c is negative 7 times t. So, right, those are the parametric equations of the line. Or, right, before we know about vector-valued functions, back in chapter 11, you would probably write them this way. But I hope you see that it's essentially the same thing. Whether you write them as x, y, and z separately as the coordinates of a point on the line, or the vector whose components start at the origin and end at the point on the line. So either way, it's the same thing, right? Okay. Okay, so I'll skip 16. It's very similar. Find the equation of a tangent plane. And number 17 is interesting. Functions, say f of xy, right, that satisfy Laplace's equation. So Laplace's equation has to do with this symbol. So this is the gradient symbol, right? It's del. However, it's squared. We'll talk about that when we get to chapter 15, I think. But for now, the definition of this is that it's the second partial derivative of f with respect to x, and then x, plus the second partial derivative of f with respect to y, then y. Or you can also write it as fxx plus fyy, right, equals 0. So that's Laplace's equation. Okay, so any function that satisfies that equation is called harmonic. It is a harmonic function. For reasons that we won't get into, but if you take say, maybe a more advanced course in electromagnetism, or even an advanced mechanics course, you may come across Laplace's equation and why the functions are harmonic. Right? But in any event, we just want to show that the given function, f of xy, e to the x times sine y, is harmonic. And I just saw a really good video about this, and maybe I'll post it in the description here, or maybe even in the on Blackboard. In any case, right, we just want to show that this is harmonic. Right. So what do we have to show? Well, we have to take the second partial derivatives and then add them up and then see if they equal 0, right? So we have to show this equation. Right? Does it equal 0? If it doesn't, then it's a bad question because then it would not be harmonic. So it better equal 0 if this is a good question, right? So we'll start with the first derivative with respect to x. It's just e to the x sine y. And so the second derivative will be e to the x sine y. And so the third derivative, right, we don't need that here, but it's the same thing. Remember, the derivative of e to the x is e to the x. So you keep taking derivatives and you're going to end up with the same thing. Okay, but we needed the second derivative, right? So now the first partial derivative with respect to y, well, the derivative of sine of y is cosine of y. So e to the x times cosine of y. And then the second partial derivative with respect to y, remember e to the x is a constant, but the derivative of cosine is not sine, it's negative sine. Okay, now let's add them up. Take the second x partial plus the second y partial, and what do we get? We get e to the x times sine y plus a negative e to the x times sine y. Well, it's like 5 minus 5 is 0, right? Whatever this is, when you subtract itself, you just get 0, which is what we wanted to show, right? That this is correct. So, therefore, f is harmonic. It is a solution to Laplace's equation. Okay. Now, the much harder question is, right, solve Laplace's equation. In other words, find all functions, right, f of x, y, that solve this equation. Okay. So that's not something we're going to do here because that's a much harder question. In fact, I don't think you can even do that in general, right? Usually what you need in addition to this is something called a boundary condition. Or maybe you can do it in general. I don't know. But usually you impose a boundary condition, right? So this is for a course in partial differential equations. So if you already took the elementary differential equations course, you probably didn't do this because these are, right, this is a partial differential equation because it involves partial derivatives. So that's more like a second course in differential equations. That's a much higher level course. You know, and some of you may end up taking that, some of you may not. If you take a course in mathematical methods, say in engineering, you may come across some of this material as well. And number 18, find the points on the unit sphere. So this is just the sphere of radius 1. Okay, so pretend the radius is 1 here, where the tangent plane is parallel to the plane. So the plane is 2x plus y minus 3z equals 2, or minus 2 equals 0, doesn't matter, right? So that plane, that might be over here somewhere, right? So pretend this is a plane just coming out of the board, right? I mean, it does have, right, it's two-dimensional. But I'm trying to make a point here, right, that the plane, of course, is not a tangent plane. We're looking for the tangent plane that's actually parallel to this plane. Okay. So we're looking for this plane here. Okay. So how are we going to do that? Well, what's true about the given plane here? I'm trying to draw a vector perpendicular to that plane. So that's easy to find. That's your A, B, and C, right? 2, 1, negative 3. Okay, and of course it's a much longer vector, but you get the point, right? It's longer than this. Well, if that vector is, right, normal to this plane, it's got to be normal to this plane as well. Right? And again, we can scale it, we can make it longer or shorter, but the direction is still perpendicular to the plane. Right? So there's a very easy trick to this. Just move this vector, right? Remember, you can move this vector anywhere you want. It doesn't even have to be on the plane. It could be way out here or over here. Or how about if we start it at the origin and make the vector end at this point on the sphere, right? So that point will be a point where we have the tangent plane to the sphere, and it'll be parallel to the given plane. Okay. Now, this is a little bit misleading here because you might suspect that, oh, if I put the initial point at the origin, then the terminal point will just have coordinates 2, 1, negative 3. Right? But that's not the answer, right? That's not a point here. And the reason is because, right, this vector is a lot longer than that, right? This vector will go way up over here now. Remember, the sphere has radius 1. This vector has magnitude what? So the magnitude of n is going to be the square root of 4 plus 1 plus 9. So 14, square root of 14, right, which is clearly bigger than 1. And that's why this vector just goes way out up here. So what are we looking for? We're looking for a vector, right, of magnitude 1 so that the radius is 1 for the sphere, right? So we know how to do that, right? We know how to find a unit vector, say u, in the same direction as n, just divide by its magnitude. Right? So we have a vector 2 over the square root of 14, 1 over the square root of 14, and negative 3 over the square root of 14. Okay, so that's this red vector here, right? That's the vector I'm calling u. So this vector here is u. And so now the terminal point of u will be the coordinates of this point here. I'll call that point P. That's on the sphere as well as on the tangent plane. Okay, so again, don't bother rationalizing the denominator. You can if you want, but it's not necessary. Okay, so that's the answer, right? Find the points on the unit sphere where the tangent plane is parallel to the given plane. Now, it does say points, right? So yeah, we're not done yet. Points. There's actually 2 points here. So which one did I miss? I missed the one on the opposite side. There's also this. Oops. Sorry. Yeah. So there's this tangent plane here that's also parallel to the given plane. And of course, it's parallel to this plane, right? Yeah. So we need this point here. But notice that it's a vector in the opposite direction. Same magnitude. Magnitude is still 1. So in the opposite direction, you just get the negative components, right? So our point, I guess I'll call this point Q here. All right. Our point Q will have coordinates negative 2 over square root of 14, negative 1 over the square root of 14, and then z will be positive 3 over the square root of 14. So those are the 2 points on the sphere where the tangent plane is parallel to the blue plane. The blue plane is the one that's 2x plus y minus 3z equals 2. Okay, so that's the quickest way, I think, to get these points here. Just take the vector, move it around so that its initial point is the origin, and then just normalize it so that you get a vector with radius 1 or with magnitude 1 that matches the radius of the sphere. Right? Okay. And if it's a sphere of radius 2, okay, then just double all the components, right? If it's a sphere of radius square root of 7, then multiply each of the components by square root of 7, and so on. Right? But I think we made it easy by just making it the unit sphere of radius 1. Right, number 19. Find all critical points of the function, and I just copied it down here, f of xy equals x cubed minus 6xy plus 8y cubed. So we want the critical points, and then for each critical point, we want to determine whether it's a maximum, minimum, or saddle point. And hopefully we don't get any degenerate critical points where we won't be able to tell. Because remember, if d is equal to, well, so remember what the second derivative test says. We need to find d, which is this construction, fxx, fyy, minus fxy squared. And if d is positive, then we get a maximum or minimum. Well, we get a maximum if the second derivative is negative, right? Because if the second derivative is negative, it's concave down. If the second derivative is positive, we get a minimum, right? If d is negative, then we don't bother with a second derivative. We automatically just get a saddle point. And finally, if d is 0, then we have no idea. So hopefully that won't happen here. All right, before we can do any of that, we need the critical points. And to find the critical points, you take the gradient, which is, again, just both partial derivatives. So 3x squared minus 6y for the I component. And then negative 6x plus 24y squared for the j component, right? And so we're looking for where the gradient is the 0 vector. So we just take both partial derivatives and set them equal to 0. Squared equals 0. And you get a system of 2 equations, 2 variables, right? Not too bad here. Except they are nonlinear equations, but I think we can do this okay just by substitution. In fact, just to make it easier, can we divide the first equation by 3? And then the second equation by 6? You don't have to, but that might make it easier. So we have to solve this system of equations. So I'll call this equation 1 and equation 2. I'm going to start with I changed my mind. Equation 1. If we solve for y, we get 2y is equal to x squared. And in fact, we can just square that, right? If we square both sides, we get 4y squared is equal to x to the 4th. So for equation 2, negative x plus 4y squared is really just negative x plus x to the 4th. And we can solve that equation by factoring out an x. So we either get x equals 0 or x equals 1, right? The cube root of 1 is 1. There are 2 other solutions to this equation, but they're imaginary, so we don't care, right? So 2 x's, and then let's see, what was y? 2y was x squared, right? So y was x squared over 2. So if x is 0, y is 0. And if x is 1, y is 1/2. Right, so it looks like we get 2 critical points. Right, I'll call them A and B. So point A is just the origin, 0, 0. And point B, that's points, right? Point B is 1/2, 0. No, sorry, 1, 1/2. I'm getting confused here. Yes, x equals 1, y equals 1/2, right? So those are our 2 critical points. And, right, so now we just figure out whether we get a maximum, minimum, or neither for each. So let's start with point A. We need the second derivatives, right? We took the first derivatives. How about the second derivative? So fxx is going to be what? It's going to be 6x minus 0, right? So just 6x. fxy is going to be negative 6. And fyy, the second y partial derivative, is going to be 48 times y. Right, so that means d is going to be, well, 6 times 48 is 288 times x times y, minus negative 6 squared is 36. Okay, so that's d. So now let's apply that to point A. In other words, plug in x equals 0, y equals 0. You just get negative 36. And if d is negative, we don't have to bother with the second derivative. Right, the point 0, 0, was it 0, 0, 0, will be a saddle point. Right, so neither a minimum nor a maximum. Great. On to point B, right? So d, when x is 1/2, sorry, x is 1, y is 1/2. So this is 288 times 1 times 1/2 minus 36. So 144 minus 36 is, I want to say 108, although it doesn't matter as long as it's positive. Yeah, it is 108, but it's a positive, right? So when d is positive, we have a maximum or a minimum. Right? Which is it? So let's look at the second derivative with respect to x. If you plug in the critical point, 1, 1/2, we get 6 times 1, which is 6. 6 is positive. Positive means concave up, and that means we have a minimum, right? So the point, 1, 1/2, and I guess what's the z value here? 1 minus 3 is -2. -2 plus 1 is -1. So, yep, 1, 1/2, -1 is a relative minimum point. Right. So, yeah, think of like a paraboloid here, right? The bottom of the bowl here is your relative minimum. So we have one saddle point at 0, 0, and one minimum at 1, 1/2. And I think that answers the question. So that's number 19. Number 20. Find the absolute maximum and minimum values of the function f of xy equals xy squared on the disk of radius square root of 3. So that's x squared plus y squared is less than or equal to 3. Right, so I drew the disk here, so this is 1, this is 2. Square root of 3, if you remember, is about 1.7, so that's the radius. Right. So yeah, this is not looking for relative maximum minimum, this is looking for absolute maximum minimum, because this is a closed and bounded region of the xy plane. So we are guaranteed to have both a maximum value and a minimum value. Right. The hard part is finding them. Right? And we do it the usual way. We want to find the critical points, if there are any, critical points inside of D, right? Inside the region D, right? And then we also look at the boundary, right? Which is the light green circle here, right? So yeah, the boundary of the disk, the boundary of D is just the circle x squared plus y squared equals 3. So we'll look at that later. Let's first find the critical points. So the x partial derivative is just y squared. Set that equal to 0. The y partial derivative is 2xy. Set that equal to 0. Well, if y is 0, right, then that's the x-axis here. So every point on here, I think, is a critical point. That's a whole lot of them, right? So if 2xy equals 0, that means either x is 0 or y is 0. We already know y is 0. But x equals 0 would be the y-axis. But we already know y is 0, so x doesn't have to be 0 then, right? Right. In other words, if you plug in a point, say 0, 1, into the gradient, what do we get? We get the vector 0, 1, which is not the 0 vector. Right. So yeah, it's only on the x-axis. It's only when y is 0. Right. If x is 0, y would have to be 0, so that's 0, 0. But if x is 0 and y is not 0, then that's not gonna be a critical point, right? Okay. But the nice thing about this is that every one of these points, when you plug it into the function, right? It doesn't matter what x is, y is 0. We get x times 0 squared, which is 0. So the value of the function everywhere on this line, right, z is just 0. I'll call it f, right? F is just 0 here. Okay. So that takes care of the critical points, right? Now we look at the boundary. Right? Now we look at the boundary. And, right, so the boundary is x squared plus y squared equals 3. So the trick here is to solve for y, right? Y squared is just 3 minus x squared. Right? Why didn't I solve for x? Because notice the function f of xy is xy squared. If I solve for x, I would have to take the square roots. In fact, I would have to take plus or minus the square root, which is a nuisance. But here, since I have y squared, I can just plug that in, and we get x times 3 minus x squared. So what I've done is I've reduced it down to a function of just x. It doesn't matter what y is now, right? Okay, so anywhere on the boundary, on the circle itself, right, this is only going to be true, this is valid only for points on the circle, right, but not inside the circle, not on the disk, right? Okay, right, because yeah, we're looking at the boundary here, the circle, boundary equals circle. Okay, so as a function of x, this is 3x minus x cubed. We can take the derivative of that pretty quickly. And we can find the critical numbers, as you did in Calc 1. We just get x is equal to plus or minus 1. So let's look at x equals negative 1. What's y going to be? Well, y squared is going to be 3 minus 1 squared. 3 minus 1 is 2. So y is going to be plus or minus the square root of 2. And if x is positive 1, yep, you get the same thing, right? 3 minus 1 is 2. So, equals to 2. And then, so y is going to be plus or minus the square root of 2. So we get 4 points on the boundary, right? Negative 1 square root of 2. Negative 1 negative square root of 2. Positive 1 square root of 2. And positive 1 negative square root of 2. Where are those points? Well, if x is 1, square root of 2 is, right around here. Is that right there, right? So that's where both are positive. Here's where x is positive and y is negative. And here's where x is negative, y is positive. And here's where they're both negative. So, yeah, so this is 1 square root of 2. This is 1 negative square root of 2. This is negative 1 positive square root of 2. And this is negative 1 negative square root of 2. Okay. So 4 possibilities here. What do we do with these? Well, we want to know which one is the biggest and which one is the smallest. Right? So plug them into the function, find z. This is just going to be negative 2. Let's do, this is also negative 2. And when x is 1, I think we just get positive 2 in both cases. So we have a choice between negative 2 and positive 2. We want the maximum and the minimum, right? The maximum would be 2, the minimum would be negative 2. 0, which are, right, these numbers on the x-axis give you z equals 0, is right in the middle. So 0 is not a minimum or a maximum. So yeah, the maximum value of f, maximum value of f, right, on the disk D is 2, and it occurs at 2 points here. It occurs at 1 square root of 2 and negative 1, no, sorry, positive 1 negative square root of 2. Right. And finally, the minimum value of the function f squared, right, on the disk D is going to be -2. And that occurs at the 2 points where x is negative. -1, right? Yep, so on this disk, right, at this point here and this point here, f is going to be equal to 2. And at, oops, I should use a different color here. How about green? So at this point and this point, this f is going to be -2, and same thing here. Okay, so that does it. Maximum value is 2, the minimum value is -2. Not much else to show here. So yeah, so fairly routine example. Again, when you're looking for the absolute maximum and minimum, and as opposed to the relative maximum minimum, you also have to worry about the boundary, the circle itself. So as it turns out, the maximum and the minimum values occur on the circle itself, on the boundary, not inside, not in the disk. But again, in other examples, you might have a minimum or maximum inside the disk, in which case that would be a critical point, right, at a critical point. Okay. And I was almost going to skip this one, number 21, because, well, it's very easy. In fact, you could have done this in Calc 1, right? So yeah, I think on a test, I would pretty much insist that you should use Lagrange multipliers here. Because otherwise it's just too easy, right? All right, but maybe I'll do it both ways, right? The easy way is just to say, well, look, y is going to be x minus 3. So if I plug that in to the equation here, I get a function of x squared plus 2x minus 6 times x minus 3. Right, so you just get a quadratic function. And so take the derivative, set it equal to 0. To 4. So x has to be 2, right? And if x is 2, y is 2 minus 3, which is -1. So that's where your minimum has to be, right? So your minimum is at the point 2, -1. And the minimum value is 2 squared minus 4 times 2 plus 18. Right, which is 14, I think. Right, 18 minus 8 is 10. 10 plus 4 is 14. Okay, so this should be the minimum value. Right. And how do we know it's a minimum? Well, right, it's the second derivative is positive here. Right, it's just 2, which is obviously positive. And that means it's concave up, which means you have a minimum. Right, lowest point. Right. All right, so obviously, yeah, this is not the way I want you to do it. I want you to use Lagrange multipliers, right? Okay, so the equation for Lagrange multipliers is gradient of f equals lambda times gradient of g, gradients. And then don't forget the constraint equation, right? So the gradient of f is 2x plus 2, and then the y partial is just -6. So that equals lambda times the gradient of g. So what's g? G of x and y is just x minus y equals 3. So it's just 1, -1, right? So what do we get? We get 2x plus 2 is equal to lambda, and then -6 is equal to negative lambda. That's a 6, right? And then the constraint equation is x minus y equals 3. So 3 equations and 3 variables. And I think you can handle that, right? After all, if negative lambda equals negative 6, lambda is 6. So if lambda is 6, then 2x plus 2 is equal to 6, which means 2x is equal to 4, which means x equals 2. And that looks familiar, right? Same thing. And of course, if x is 2, by the constraint equation, y is going to be 2 minus 3, right? Which is negative 1. So there you go, same answer, right? So the critical point here would be 2, negative 1. That's where the gradient is 0, right? Is the 0 vector. Oh, is it? Hang on. The gradient... No, I'm sorry. The gradient is not 0. The gradient is equal to the lambda times, right? So that's where this is true, not where the gradient is 0. Sorry. My mistake. Okay. Yeah, so in any event, when you plug in 2, negative 1 into the original function, you still get 14, I hope. Yep, 4 plus 4 plus 6 is 14. So, yep, so we minimized f, right? So the minimum value is still 14. And it occurs at the point 2, negative 1. Right? Now, so how do we know it's a minimum? Well, you can use the second derivative test if you want. Right? We did the second derivative test when we did it the other way. And you can see this way is not that much harder than the way we did it earlier, at least once you get used to it, right? Okay, so that's 21. Very routine problem. If this were on the test, I would consider this to be kind of a gift. It's almost too easy. Yeah, I cannot say the same thing about number 22. Find the minimum distance from the origin to the surface. So remember, when you have a surface, this is going to be an implicit surface, because I don't think we want to solve for y here. And I'll do minus 25 equals 0, just to be consistent. So that's our constraint equation. And the function we want to minimize is the distance. And remember, we can, yeah, I guess, I'll call it little f here. So it's going to be the square of the distance, right? It'll be x squared plus y squared plus z squared. If you want to use the square root, fine, but then you're going to have to deal with the, the exponent of 1/2 and so on. Okay, so minimize the square of the distance to the origin. So this is the square of the distance to the origin. To 0, 0, 0, right? Right. So we have two ways of doing this now, right? We can use Lagrange multipliers, or we can solve this equation for either x, y, or z. And traditionally, we would solve for z, right? We want this to be a function, s as a function of just x and y. So here's what you would do, right? You'd solve for z squared. Z squared would be what? It would be x squared plus y squared minus 25. Okay, so that's what we've been doing. And when you plug that into the function for s, the square of the distance, well, z squared is x squared plus y squared minus 25. Okay. And so simplifying it, you get 2x squared plus 2y squared minus 25. Okay. So let's see what happens, right? Now we find the critical points, right? Critical points. Right. So we take the gradient of s, right, which is the x partial of s and the y partial of s. And that's not hard, right? This is just 4x and 4y. And where is that equal to 0, 0? Only one point, right? 0, 0. The origin. Okay, well, if that's the critical point, and that's the only critical point we have, what is the minimum distance then? Well, let's see. It's just going to be s of 0, 0. And that's going to be 2 times 0 squared plus 2 times 0 squared minus 25. So we just get negative 25. Now that's not the distance. Remember, that's the square of the distance. So s is really the distance squared is negative 25. So take the square root, and we get plus or minus the square root of negative 25, which is plus or minus 5 times I, which makes no sense whatsoever. The distance is imaginary? No. No, that can't be. Okay, so what went wrong here? Right, so I don't think I did anything wrong. My mistake was doing the usual thing here, solving for z, because we usually like to write the function in terms of x and y. Okay, that's not going to work here. And the reason why that's not going to work is you can go back to the surface, right? The surface is given by this equation here. Equals 25, right? So if x and y are both 0, you get that negative z squared equals 25, or z squared is negative 25. And again, this has no real solutions. These only have imaginary solutions when the exponent is, sorry, that's a sloppy 2 here. Right, so yeah, you get z is plus or minus 5i, which is equally ridiculous, right? Yeah. So yeah, this is where most people would get stuck and say, what did I do wrong, right? I didn't do anything wrong. Unfortunately, if you solve for z here, that's what's going to go wrong, right? You're not going to get the answer this way. So if we go back to the original surface here, right, this surface up here, remember, originally I said there's nothing magical about solving for z. We could solve for x or y. So let's take this equation, x squared plus y squared minus z squared minus 25 equals 0, and solve for x, right? So x squared is going to be what? It's going to be 25 plus z squared minus y squared. Okay. And that is just as easy to plug into the distance function, or the square of the distance function, right? Which is just x squared plus y squared plus z squared. But now we know what x squared is, right? It's 25 plus z squared minus y squared, right? So that's x squared plus another y squared plus another z squared. And when we simplify that, you get 25 negative y squared plus y squared is 0, and you get z squared plus z squared is 2z squared. Okay, and that, again, that's 25, not an s, 25 plus 2z squared. So we've reduced this down to a function of just y and z. Right? In fact, it doesn't actually depend on y. It's only a function of z. So find the critical numbers, right? Instead of taking the partial with respect to x, we'll do y. That's just 0. And then the partial derivative of s with respect to z is just 2 times z. So where does that equal 0? That equals 0 when z is 0. Okay, so we never solve for y, but y can be any constant, right? Y can be anything. If the partial of s with respect to y is 0, the derivative is 0, that means, right, y can be any constant. Which I know seems weird, but we'll come back to that, right? So, okay, so z equals 0 is our critical point. What does that mean in terms of the surface? Well, in terms of the surface, right, remember what z squared was. We originally had it solved for z squared. X squared plus y squared minus 25. But if that equals 0, that tells me that x squared plus y squared is equal to 25. You know what that is, right? That's a circle. A circle of radius 5, right? So every point on this circle, right, is a critical point. So we don't just have one critical point or two critical points, we have infinitely many. Every point on that circle is a critical point. All right, and so what's the distance from the origin? Well, we could go back to the original distance formula. Actually, we don't have to here. We have, in terms of just y and z, yeah, I think you could do it either way. But in terms of y and z, this is just 25 plus 2z squared. But if z is 0, you get 25 plus 0 squared, so you get 25. And remember, that's not the distance from the origin, that's the square of the distance, right? S is d squared. But now d squared is a positive number, so you get d is plus or minus 5. Well, the distance should be positive, right? So we'll ignore the negative 5. Right? So this is the minimum distance. How do I know it's not a maximum? Well, you can use the second derivative test, or let's just think about this in terms of what the surface is here, right? So yeah, so the minimum distance is 5, and it occurs at all points on the circle, all points x, y, such that x squared plus y squared equals 25. Right. Okay. Now, what is this surface? This surface, x squared plus y squared minus z squared equals 25, is a hyperboloid. Right? It would be nice if you knew that, but you didn't need to know that, right? I mean, we solved the problem without ever knowing what that surface was. But now that we know what it is, we can sort of, I'll try to draw a very rough sketch of the picture here. Here's the z-axis, right? Here's the x-axis. Here's the y-axis. So I need to go deeper here, right? And so let's say this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2, 3, 4, and so on. Okay. So the hyperboloid will look something like this. It's in fact just a surface of revolution. So take this hyperbola and then revolve it around the z-axis here. So it'll look like this. Right. And then we'll have this piece of it over here. Right. You get the idea, right? I hope, right? I know it's a little sloppy, but it's, right, this is the surface here. So now the origin is 0, 0, 0 right here. We're looking for the minimum distance, right? We're looking for the points on the hyperboloid that are closest to the origin. So if you go way up here to this point, or way over here to this point, eventually it'll meet, right? That's not the minimum distance, right? If you go to this point, that's a bit closer. This is even closer. Or just go straight left and right. And this point, you can see, is only 5 units away, right? So this point here is, let's see, 0, 5, 0. But remember, this is a surface of revolution. So this circle that I talked about earlier here, that's this circle right here, right? And the radius is 5. So all points on the hyperboloid, on this circle here, give you the minimum distance, which is just 5 units. Every other point on the surface, right, well, you know, this down here will be a bigger circle, a bigger radius, and the distance from the origin will be, you know, even bigger than 5, obviously, right? So yeah, the further up you go and the further down you go, the bigger the circle and the bigger the distance. So inevitably, right, the minimum distance occurs when z equals 0, right? If z is any bigger than 0, you're going to get a bigger distance. So that's kind of what went wrong in our original strategy here. We eliminated z, right, when z was supposed to be 0 here. So by eliminating z, we got this equation with just x and y, and there was no way to solve, right, that equation in terms of finding the critical point, right? 0, 0 is not a critical point because when x and y are 0, that's along the z-axis. That's the axis of revolution, right? The z-axis is not part of the hyperboloid, right? That's the axis you're revolving around to get the surface here, right? So there you go, right? That solving for z here was doomed to fail. We had to solve for either x or y. I just picked x here, and it worked out. But it would have worked out equally with solving for y, or y squared. Yep, so a difficult problem if you do it the same way that we did all the other problems where we eliminated z to write it as a function of x and y. Unfortunately, that doesn't always work. Here we had to eliminate, say, x or y and solve in terms of y and z or x and z. I think we used y and z here, right? So yeah. So not a hard problem if you think of it the right way. If you get stuck, it's because you solve for z instead of x or y. So that can be an issue. Oh, one more thing. We could have used Lagrange multipliers, and I don't think we would have run into this issue at all. So if you did it by using Lagrange multipliers, yeah, you're not going to have this problem up here where it just didn't work out, right? Where you got these imaginary numbers. Okay, so just to mention that. You could have done it that way too. Okay, number 23. Another maximum minimum problem, right? In this case, find the maximum value, right? So we want to maximize this function. F of x, y, and z. And it's just ax plus by plus cz for some unspecified a, b, and c, right? So a, b, and c are just, well, they're positive numbers, let's say, although, yeah, they don't have to be. So these are just unspecified constants, right? These are constants, positive real numbers. Okay, right. Yeah, so the constraint is that the points have to be on the unit sphere, right? So that should be my g of x, y, z. So x squared plus y squared plus z squared. And you could do minus 1 equals 0 if you want, or just do equals 1. That's fine too. Right, and so we want the maximum value in terms of a, b, and c, obviously. Okay. So I suppose we could do this by solving for z, but notice that this is not z squared. And so we would have to take a square root, and you're going to get plus or minus the square root. So if it's all the same to you, let's use Lagrange. Right, Lagrange multipliers. Right, after all, taking the gradient of f, not a big deal here. You just get a, b, and c. And then taking the gradient of g, also not hard. We've done it before many times. 2x, 2y, and 2z. Okay, so when we form Lagrange's equation, the Lagrange multiplier equation, right? So here's the Lagrange multiplier equation. We're going to get a is equal to 2x times lambda, b is equal to 2y times lambda, and c is equal to 2z times lambda. Okay. So we have 3 equations, but we have 4 variables, right? The variables are x, y, z, and lambda, right? A, b, and c are not variables, right? Those are fixed constants. Those are constants, right? So we don't know what they are, but, you know, they're numbers, right? They can be any real numbers. So, of course, we have to combine this with the constraint equation to get 4 equations in 4 variables now. Okay, so solve that system of equations. And my usual strategy is to solve for lambda first. So x is just going to be a over 2 lambda. And y is going to be b over 2 lambda. And z is going to be c over 2 lambda. If we plug those into the constraint equation, what do we get? We get a squared over 4 lambda squared plus b squared over 4 lambda squared plus c squared over 4 lambda squared is equal to 1. Of course, we have a common denominator. So if you multiply both sides by 4 lambda squared, you get this. Okay. Oh, actually, we wanted lambda, right? Lambda is, so lambda squared is just a squared plus b squared plus c squared divided by 4. And if you take the square root, right, you'll get plus or minus the square root of a squared plus b squared plus c squared all over 2. Okay. So if that's lambda, what's x going to be? So let's go back to x here, right? Remember, x was a divided by 2 lambda. So a divided by 2 times lambda, which is, plus or minus. Let's go with the plus. After all, we want to maximize. The minus is probably the minimum. Although we don't know that for sure. We'll come back to that, right? Let's do the plus first, though. So this is going to be the square root of a squared plus b squared plus c squared divided by 2. So the 2 goes on top, and the 2's cancel. So x is just a over the square root of a squared plus b squared plus c squared. Right? And by symmetry, I think we can safely say that y will be b divided by the square root of a squared plus b squared plus c squared. And then z will be c over the square root of a squared plus b squared plus c squared. I mean, if you don't believe me, work it out, but I think that's it, right? So I think that's our that's our x, y, and z. Right? These are just the coordinates. Oh, I hate writing out the square root again. We know what the square root is, right? Okay. Right. So, so what's the maximum value of f? So remember what f is, right? F is just the function of x, y, and z. It's ax plus by plus c times z. So if we plug in these 3 numbers into the function, a over the square root, b over the square root, c over the square root, we get what, right? We get a times a, so a squared divided by the square root. Now notice the square root's going to be the same thing in all 3 denominators. So I'll write it out this time. But then the numerator will be, right, plus b squared plus c squared. So that's the maximum value, right, in terms of a, b, and c. Right. So I should have given this a name, right? We should have called this x0, y0, z0. Because that's the critical point at which you attain your maximum. Okay, and then there's the maximum value. Oh, we could do better than that, right? This is just the square root of a squared plus b squared plus c squared. Sorry, that's a b, not a 6, right? All right, let me try that one more time. A squared plus B squared plus C squared, all under the square root. Okay, so that is the maximum value. So this is the maximum value of f, right? And it occurs at the point x0, y0, z0, which I don't want to write out one again, but it's a over the square root of a squared plus b squared plus c squared. Oops. B over the square root of a squared plus b squared plus c squared. And then c over the square root of a squared plus b squared plus c squared. Okay. So that's essentially the point on the sphere where the value of the function is maximum. Maximum? Yeah, maximum. Oh, and I should probably come back to this question of lambda. Remember, there were two possibilities, one with a positive square root and one with a negative square root. So if lambda had a negative square root, what would happen? You would just get a negative sign for all these, right? And then your minimum value, right, would be f at, well, negative x0, negative y0, negative z0, which would just be negative square root of a squared plus b squared plus c squared. Okay. So yeah, positive for the maximum, negative gives you the minimum value. I hope everyone can read this in red here. But anyways, that wasn't the question. The question was to find the maximum value, right? The maximum value of f, and we did that down here. And yeah, so, oops. So this is the maximum value. Right. And they didn't ask where it occurs, but I wrote that down in case you're curious. Okay. So that's it for 23. And we might as well do 24. This is kind of my personal favorite problem here. You're in charge of constructing a radio telescope on some distant, newly discovered planet. To minimize interference, you need to place the telescope where the magnetic field on the planet is the weakest. And the planet is a sphere of radius 6 units, so probably not 6 miles, but, you know, a unit could be, 1,000 miles, 10,000 miles, who knows, right? But okay, so the planet is a sphere. So we might as well put the center at the origin. So x squared plus y squared plus z squared equals 36, right? So this is the surface of the planet, right? With the origin at the center, okay, so they forced that on us, right? So the origin is the center of the planet. The magnetic field strength is B. So B is usually the symbol for magnetic field. You can also use H, but I think that's the magnet. Let's not get into that, right? Let's just use B. And yes, it is a vector, but we're taking the magnitude of this, I guess, and we're getting 6x minus y squared plus xz plus 60. And to be fair, I don't think you can have a magnetic field with this function here, but I don't know. That's a trickier problem. Because, again, this is not the magnetic field as a vector, because it is a vector field. It's just a scalar field. So we're just measuring the strength of the magnetic field, not the actual direction. Okay, so, yeah, so you can get a compass, and that'll measure the direction of the magnetic field, pointing north, of course. But that doesn't tell you the strength of it, right? So you need a device to measure a magnetic field. So I think a Gauss meter or something. I don't know. All right. Anyways, all right. So this is obviously the thing we want to minimize here. Right. So the sphere. This is the constraint. We're constrained to be on the planet. Right. So we can't dig below the surface and bury the telescope. That wouldn't make much sense. And for whatever reason, right, we could put the telescope in orbit, right, like the Hubble telescope. But no, here we want it on the planet itself. Okay, and this is the function we want to minimize. Right, so that's b. That's our function. Okay, so again, we have two ways of doing this. We can use Lagrange multipliers. That's a reasonable way to do it. It's probably easier, though, if we just substitute. And again, the usual thing to do here is to take your constraint equation and solve for z so that we get the magnetic field strength in terms of x and y, right? But we learned from the problem, not the last problem, but the one before that, that you don't always want to solve for z here, right? So look at the form of b. Look at the function b, right? We have 6x plus xz minus y squared. The only term that has a y squared in it, that has a square in it, is the minus y squared. So it's probably better to solve this equation for y, or rather for y squared. When you solve it for y squared, you get 36 minus x squared minus z squared. Okay, so yeah, rather than solve for z, why don't we solve for y? And then that gives us the magnetic field strength as a function of x and z, because we're eliminating y, right? So this will be 6x minus y, but y, remember, is 36 minus x squared minus y squared, right? Plus xz plus 60. Obviously, the 60 is not going to matter here. It's just some constant. So, this is the function. We've reduced it down to two variables, x and z, and there's not a lot we can do to simplify this. 60 minus 36 is 24. We get plus 6x minus x squared minus, oh, wait a minute, minus a negative x squared. So plus x squared plus y squared, and then plus x times z. Right, because you're subtracting y squared. This minus sign is in front, so that gets distributed. All right, just making sure. Okay, so next step is find the critical points, right? Take the gradients, the two partial derivatives, and set them both equal to 0. So partial of b with respect to x, or b sub x, is 6 plus 2x plus z. Oh, wait a minute. Hang on. Why is there a y squared here? That doesn't make any sense. It's, yeah. Sorry, it's z squared, right? Y squared is 36 minus x squared minus z squared. So change these two y's to z's. That was a close one. Yeah, so this should be z squared here, and this should be a z squared. It's not a function of y anymore. We should have eliminated y. Okay, anyways, the partial, back to the partial with respect to x. So we get 6 plus 2x plus z, and we'll set that equal to 0. And then the z partial, right? So bz is going to be 2z plus x equals 0. So there you go, right? Two equations and two variables. And in fact, they're linear equations, so really this should not be that hard. Let's just substitute, right? Let me make sure I got this right, right? It's 2z plus x. I think that's the derivative with respect to z, right? Yeah, okay. So x is just negative 2z. And if x is negative 2z, we get 6 plus 2 times negative 2z plus z equals 0. And we can solve that for z. Z minus 4z is negative 3z, which is negative 6. So z is 2. And if z is 2, x is negative 4. And if x is negative 4 and z is 2, what's y? Well, remember, y squared from the constraint equation is 36 minus x squared minus z squared. So this is 36 minus negative 4 squared minus 2 squared. So 36 minus 16 is 20, and 20 minus 4 is 16. So that's y squared, which means y is, well, plus or minus 4. And I think y could be positive 4 or negative 4. So we don't know which it is yet. So there we go, right? So the question is, where should you place the telescope? Well, these are the coordinates, right? I mean, these are the rectangular coordinates. You can always convert them to, longitude and latitude. In fact, that's a pretty good problem to do. We can look at that later. So place the telescope at the point, well, either at point negative 4, 4, 2, or at the point negative 4, negative 4, 2. And you'll see it does not make a difference, right? Whether we use a positive 4 or negative 4 for y, remember what b was. It's 6x minus y squared plus xz. So 6 times x minus y squared, right? You're squaring y, so positive or negative doesn't matter. Plus xz. So plus negative 4 times 2. And then plus 60, if I remember right. In fact, that'll make it positive. All right, so negative 24, negative 24 minus 16 minus 8 plus 60 is 12. Okay. So, yeah, you place the telescope at either of these locations on the planet, and the minimum magnetic field strength, again, the direction we don't know, but the minimum magnetic field strength, right, is B is equal to 12. We didn't give units here, right? So it could be 12 Tesla. That would be a very strong field, at least relative to, Earth's magnetic field. I don't think is anywhere near that strong, at least where we are. Or 12 Gauss. Whatever the units are. So I didn't give units, so it doesn't matter. That's for a physics course. Yep, so what is the magnetic field strength at that location? It's got to be 12. So you can, right, and you can check if you pick any other point on the sphere and measure its magnetic field, or right, plug into this function, you'll see it should be bigger than 12. Probably bigger than 12, right? Or it has to be bigger than 12. Anyways, yeah, so that should do it. So if you did use Lagrange multipliers, it's not quite this straightforward. It's a little bit more complicated because you got to look at some possibilities where, lambda 0 or lambda is some other value. It's doable, but it's not quite as straightforward as just substitution here. So, if you want a challenge, right, do this using Lagrange multipliers. So use Lagrange multipliers to do the same thing. And you should get the same answer eventually. But this is more difficult, right? It's not quite as easy, right, in my opinion, as this. All right, that's it. That should do it. Again, I skipped a few problems, but I think I did most of the more difficult ones. And yeah, best of luck.